There is a wall around humanity. You cannot see it. You cannot touch it, but it is there. 16 billion light years in every direction, and we will never cross it. Scientists calculated exactly how far humans can travel through space. The answer is not what you expect. We can see 94% of the universe through our telescopes. We will never reach any of it. The expansion of space itself is pulling everything away faster than we can chase it, and it gets worse from there. If this changes how you think about our place in the cosmos, subscribe and come with us. Chemical rockets are the only way humans travel through space right now. Every spacecraft we built, every mission to the moon, every probe sent to the outer planets, all of them burn fuel the same way fireworks do. A controlled explosion pushes mass out the back, and the rocket moves forward. Simple physics from the 1600s. We have refined this technology for decades. We made it incredibly efficient. It is still hopelessly inadequate for the stars. Think about your car for a moment. Fill the tank, and you might drive 400 miles. Now imagine needing enough fuel to drive to the nearest star. You would need a fuel tank bigger than Earth itself. The rocket equation is merciless. For every pound of spacecraft, you need exponentially more fuel. Double your fuel, and you barely increase your speed. Triple it, and the gains shrink even further. The mathematics spiral into impossibility fast. The space shuttle, one of the most advanced machines ever built, weighed 2,000 tons at launch. Most of that was fuel. The actual shuttle orbiter weighed just 78 tons. That fuel got astronauts to low Earth orbit, 250 miles up. That is the distance between New York and Boston. The nearest star is 25 trillion miles away. You start seeing the problem. Scientists tested every chemical combination imaginable. Liquid hydrogen and oxygen give the best performance we can get. That propulsion system powered the Apollo missions. Those rockets reached speeds of 25,000 miles per hour. Sounds fast until you calculate the journey time. At that speed, reaching Proxima Centauri would take over 100,000 years. Longer than human civilization has existed. Longer than our species learned to speak. NASA engineers know these limits better than anyone. They have run the numbers 1,000 times. Chemical rockets can never break this barrier. The energy density is too low. The mass ratios are impossible. We are trying to cross an ocean in a rowboat. The ocean is made of vacuum and stretches beyond comprehension. But here is where it gets stranger. Even if we solved the fuel problem tomorrow, even if we invented a magical propellant that weighed nothing and burned forever, we would still face something worse. Something that makes chemical rockets look like a solvable puzzle. The universe itself is working against us, and the next barrier does not care about our engineering at all. December 24th, 2024. A spacecraft named Parker Solar Probe broke the record for the fastest human-made object ever. 364,621 miles per hour. Fast enough to circle Earth in under 4 minutes. Fast enough to reach the moon in less than 40 minutes. Fast enough to cross the entire solar system in months instead of years. This speed sounds like science fiction, but it is real, confirmed by NASA tracking stations across 3 continents. The probe achieved this velocity by falling toward our star, using gravity like a slingshot. 7 times it dove close to the burning surface. Each pass added more speed, more momentum. Each loop brought it closer to the maximum possible. Engineers celebrated this achievement. They had every right to. Parker Solar Probe represents the absolute peak of current propulsion technology. Nobody has gone faster. Nobody will go faster using gravity assists and chemical propulsion. We reached the ceiling. Now calculate what this record means for interstellar travel. Proxima Centauri sits 4.2 light-years away. That is 25 trillion miles. At Parker's record speed, the journey would take 7,000 years. 7,000. Your descendants, 280 generations from now, would arrive at the destination. They would not remember Earth. They would not remember you. Their language would have changed beyond recognition. Their culture would be alien to yours. The mathematics are brutal and final. Even our fastest achievement is pathetically slow on cosmic scales. Imagine running at full sprint and discovering you need to cross an ocean. That is where we stand. That is what the numbers tell us. Every physicist who works on this problem knows the truth. Speed records mean nothing when the distances are measured in light years. But the speed itself is only half the story. Parker's solar probe is a small scientific instrument. No crew, no life support, no water or food or air, just cameras and sensors wrapped in a heat shield. Scale that up to a ship carrying humans, and the speed drops dramatically. Mass kills velocity, always. A crewed spacecraft would weigh thousands of tons. Food for the crew, water recycling systems, radiation shielding, living quarters, medical equipment. All of that mass has to be accelerated. The fuel requirements explode beyond anything we can build, beyond anything physics allows with chemical propulsion. The Parker mission proved what engineers suspected. We can touch incredible speeds in our solar system. We can master gravity assists. We can build machines that survive proximity to our star. None of it matters for the stars beyond. The gap between our best and what we need is not a gap. It is a chasm wider than space itself, and speed is just the beginning. Something else waits in the void between stars. Something invisible that makes the journey even more dangerous than distance alone. 7 months. That is how long it takes to reach Mars using current propulsion systems. 7 months inside a metal tube barely bigger than a small house. 7 months breathing recycled air. 7 months with the same 5 people. 7 months knowing that any mechanical failure could mean death in the void. NASA calls this a Mars transit window. Astronauts call it something else entirely. The journey to Mars is not like flying to another city. You cannot turn around. Once the trajectory is set, you are committed. Earth and Mars orbit at different speeds. Launch windows open only once every 26 months. Miss your arrival window, and you might drift past Mars entirely. The navigation has to be perfect. The timing has to be flawless. One mistake and the mission becomes a tomb. Engineers designed the spacecraft with every system backed up 3 times. Oxygen generation, water recycling, temperature control, communication arrays, food storage, medical equipment, waste processing. Every critical function has redundancy, built on top of redundancy. The systems still fail. Mars 500, a ground simulation in Russia, showed what happens to crews in isolation. After 500 days, relationships fractured, communication broke down. Small disagreements became bitter conflicts. And that was on Earth, where help was always nearby. In space, there is no rescue, no emergency return, no calling for backup. The crew is alone in a way humans have never experienced before. Early Mars missions will test this psychological limit more than the physical one. Can people stay sane for 7 months in a confined space? Can they work together under constant stress? Can they handle the knowledge that the void is inches away, separated only by thin metal walls? The radiation exposure during the journey is another nightmare. Mars has no magnetic field like Earth. The spacecraft has no magnetic field either. Cosmic rays pass through the hull like it is made of paper. Every day in transit increases cancer risk. Every solar flare threatens acute radiation sickness. Astronauts on the International Space Station get some protection from Earth's magnetic field. Mars-bound crews get none. SpaceX claims they can reduce the transit time to 5 months with better propulsion, maybe even 4 months with optimal trajectories. The improvements help, but they do not solve the core problem. Mars is our neighbor. It orbits next door on cosmic scales. If 7 months breaks human endurance, what happens when the journey takes decades? What happens when the destination is light years away instead of light minutes? The Mars mission is a test. a proof of concept for longer voyages. If we cannot handle 7 months to Mars, we have no hope for the stars. Engineers know this. They study every failure, every breakdown, every psychological crisis. They are learning what humans can endure. The answer so far is sobering. We are fragile. We are vulnerable. We are barely capable of reaching our planetary neighbor. What comes next makes the Mars journey look like a weekend camping trip. Space is not empty. Between the stars, between the planets, even in the apparent vacuum near Earth, particles move at speeds approaching light itself. We call them cosmic rays. They are not rays at all. They are the nuclei of atoms stripped of electrons, protons, helium nuclei, iron atoms moving at 9/10 the speed of light. They carry energy levels that should not exist in nature. When these particles hit human tissue, they do not just damage cells, they shred DNA molecules. They create cascading chemical reactions. They punch holes through cell walls and destroy genetic information that took billions of years to evolve. A single iron nucleus traveling at relativistic speed can tear through 30 cells in a straight line, each one damaged beyond repair, each one triggering potential cancer. On Earth, we never think about this. Our planet's magnetic field deflects most cosmic rays before they reach the surface. The ones that make it through hit the atmosphere. Air molecules absorb the energy. Secondary particles rain down, but the dangerous primaries never touch us. We live inside a protective bubble we did not build and barely understand. Step outside that bubble, and the radiation wall appears. Astronauts on the International Space Station experience 10 times more radiation than people on the ground. They stay for 6 months, maximum. Their lifetime cancer risk increases by 3%. 3% for 6 months. Now calculate decades. Calculate the journey to another star. The numbers become lethal fast. NASA scientists measured radiation during the Curiosity rover's trip to Mars. 253 days in transit. The accumulated dose equaled 660 chest X-rays. That was for an unshielded robot. A human making the same journey would face serious health consequences. Double the trip for a round journey, and you approach career radiation limits set by space agencies. Limits designed to keep cancer risk below 3%. Go beyond those limits, and you are gambling with your life. Galactic cosmic rays are worse than solar radiation. Our star throws out particles during flares, but those particles are predictable. We can shield against them with enough mass. Galactic cosmic rays come from outside the solar system. They are the remnants of supernovas, exploded stars that released more energy in seconds than our star will produce in its entire lifetime. That energy accelerated particles to impossible speeds. Those particles have been traveling through space for millions of years. They are still lethal. Shielding against these particles is nearly impossible. Add more metal to the spacecraft, and something strange happens. The cosmic rays hit the metal and create secondary radiation. Sometimes the secondary radiation is more dangerous than the primary impact. Aluminum, the material we use for most spacecraft, is particularly bad at stopping cosmic rays. It creates showers of secondary particles. Polyethylene works better, but you would need walls several feet thick. The mass becomes prohibitive. The spacecraft becomes too heavy to launch. Scientists discovered something alarming during experiments with cosmic ray exposure. The particles do not just increase cancer risk, they damage the brain. Mice exposed to simulated cosmic radiation showed cognitive decline, memory problems, decision-making failures. The particles destroyed neurons and triggered inflammation. Human astronauts on long missions might arrive at their destination with impaired mental function. They might not remember why they went. They might not be capable of completing the mission. There is no solution to this problem yet. Every proposal has fatal flaws. Magnetic shielding requires enormous power. Water shielding adds too much mass. Faster ships reduce exposure time, but require propulsion systems we cannot build. We are trapped. The radiation wall stands between us and the stars, and we have no way through it. But assume we solve it somehow. Assume we build shielding that works. The next barrier is even stranger. Somewhere in the Milky Way galaxy, a star 50 times more massive than ours is collapsing. The core implodes in less than 1 second. Temperatures spike to 100 billion degrees. Pressure exceeds anything in normal matter. The outer layers rebound and explode outward at 30,000 miles per second. Light from the explosion will not reach Earth for another 1,000 years. The cosmic rays it creates are already here. Supernovas are the most violent events in the universe. They release more energy in 10 seconds than our star will produce in 10 billion years. That energy has to go somewhere. It accelerates every particle in the explosion to relativistic speeds. Protons, neutrons, heavy nuclei like iron and nickel. These particles spread through the galaxy at speeds approaching light. They travel for millions of years. They never slow down. They never stop. Scientists confirmed this in 1962. Detectors on high-altitude balloons measured cosmic rays hitting Earth's atmosphere. The energy levels were incomprehensible. Single particles carrying the kinetic energy of a baseball thrown at 60 miles per hour. One particle, the size of an atomic nucleus, moving so fast that time itself slowed down from the particle's perspective. These were confirmed to come from supernova remnants. Our galaxy produces about 3 supernovas per century. Each one creates a new wave of cosmic rays. The particles spread outward in expanding shells. Earth sits inside shells from supernovas that exploded 10 million years ago, 20 million, 50 million. The galaxy is filled with overlapping shells of radiation. There is no safe path through them. There is no gap in the coverage. Every cubic meter of space between the stars is bathed in high-energy particles. The particles that hit Earth are bad enough. Our magnetic field blocks most of them. The ones that make it through are weakened by the shield. In interstellar space, there is no magnetic field. The particles hit at full strength. A spacecraft traveling to another star would pass through the most intense radiation environment imaginable. The crew would be exposed to particle energies that do not exist anywhere else. Some cosmic rays are even stranger. Ultra-high-energy cosmic rays carry energy levels that break our understanding of physics. Single particles with more energy than a professional tennis serve. Nobody knows how they get accelerated to these speeds. The physics does not work. Supernova remnants cannot explain them. Entire galaxies might be responsible. Black holes, devouring stars, colliding neutron stars. The sources remain theoretical. The particles are real. Detectors confirm them regularly. These ultra-high energy particles are rare. One hits each square kilometer of Earth's atmosphere per century. Sounds safe until you think about interstellar journeys. A spacecraft traveling for decades crosses trillions of cubic kilometers of space. The probability of getting hit becomes certain. One particle punching through the hull, one particle hitting a crew member. The damage would be catastrophic and instant. NASA built radiation detectors on every deep space probe. The data they send back is disturbing. Radiation levels spike randomly. Solar storms cause some spikes. Galactic cosmic ray bursts cause others. The interstellar medium is not calm. It is not predictable. It is filled with radiation hazards we cannot forecast or avoid. Planning a safe route through interstellar space is like planning a safe route through a minefield. The mines are invisible. They move randomly. They never run out. Biological systems did not evolve for this environment. Every organism on Earth developed inside the protection of our magnetic field and atmosphere. Take that protection away, and cells start dying. DNA starts breaking. Repair mechanisms get overwhelmed. Cancer rates spike. Organ systems fail. We are creatures of a protected world, trying to venture into a hostile galaxy. The numbers paint a grim picture, but what waits next is the only reason Earth is still alive. Deep inside our planet, liquid iron churns in massive currents. The outer core rotates at different speeds than the inner core. This motion generates something invisible that saves every living thing on the surface. A magnetic field that extends 37,000 miles into space. A bubble of protection we cannot see but cannot survive without. This field deflects charged particles. Cosmic rays hit the field and curve away. Solar wind particles spiral along magnetic field lines toward the poles, creating auroras instead of tissue damage. The field is not perfect. Some particles leak through, but it blocks 90% of the radiation that would otherwise sterilize the planet. Mars lost its magnetic field 3 billion years ago. Its atmosphere stripped away. Its surface became a frozen desert. Earth kept its field. Life survived. Scientists measured the field's strength using satellites. It fluctuates constantly. Solar storms compress it on the day side. The night side stretches into a long tail. The field is strongest at the poles and weakest at the equator. Astronauts on the International Space Station orbit inside this protective bubble. They still receive 10 times more radiation than people on the ground. They are just barely inside the shield's reach. Leave Earth's orbit, and the protection drops dramatically. The Moon has no magnetic field. Apollo astronauts were exposed to deep space radiation for the first time in human history. They got lucky. No major solar storms erupted during their missions. A single large flare could have delivered lethal radiation doses. The crew would have died before reaching home. NASA knew the risk. They went anyway. Mars-bound spacecraft leave Earth's magnetosphere completely. The field extends about 40,000 miles from Earth's center. Beyond that, it fades to nothing. Spacecraft traveling to Mars spend 7 months in unshielded space. The crew becomes vulnerable to every cosmic ray, every solar particle event, every source of radiation that the field normally blocks. The cancer risk calculations assume perfect shielding. Reality will be worse. Interstellar spacecraft would spend decades or centuries without any magnetic protection. Engineers proposed building artificial magnetic fields around ships. The power requirements are staggering. Generating a field strong enough to deflect cosmic rays requires megawatts of continuous power. Solar panels cannot provide that in deep space. Nuclear reactors could, but the mass increases dramatically. Every kilogram of shielding reduces payload capacity. Every kilogram of reactor fuel is one less kilogram of supplies. Some researchers suggested another approach: travel during solar maximum, when our star's activity is highest. The solar wind is stronger during these periods. It creates a temporary shield that pushes galactic cosmic rays away from the inner solar system. The effect is real, but limited. It only works near our star. Once the spacecraft travels beyond a few astronomical units, the protection vanishes. The strategy might help for journeys to Mars. It does nothing for interstellar missions. The field we take for granted is a miracle of planetary physics. Earth's size is perfect. Too small, and the core would have frozen billions of years ago. Too large, and the gravity would crush the field into something different. The rotation rate matters. The composition matters. Everything has to align perfectly. Only one planet in our solar system got the combination right. Only one planet can sustain complex life on the surface. Leaving that protection means accepting radiation levels that evolution never prepared us for. It means betting that technology can replace billions of years of planetary shielding. It means trusting that we can engineer our way past a problem that killed Mars. The confidence of engineers is admirable. The physics is unforgiving. We have barely begun to understand what we are up against. And even if we built perfect shielding, even if we replicated Earth's magnetic field around our ships, there is still a limit that nobody can engineer away. NASA sets a number for every astronaut, a lifetime radiation dose limit. Cross that number, and you never fly again. The limit is calculated to keep your cancer risk increase below 3%. 3% might sound small. It is not. It means 3 in 100 astronauts will develop fatal cancer directly from their radiation exposure. Those odds are considered acceptable. Barely. The limits vary by age and gender. Younger astronauts have more years ahead to develop cancer, so their limits are lower. Women face stricter limits than men because radiation increases breast and ovarian cancer risk more than prostate cancer. A 30-year-old woman can accumulate about 600 millisieverts over her career. A 50-year-old man can take twice that. These numbers come from decades of research, medical studies, cancer registries, bomb survivor data from Hiroshima and Nagasaki. The science is solid, the limits are real. 6 months on the International Space Station exposes astronauts to about 80 millisieverts. That is equivalent to about 800 chest X-rays. Do that twice, and you have used up a quarter of your career allowance. 3 missions, and some astronauts hit their limits. Their careers end, not because they want to stop, not because they cannot do the work, because the radiation caught up with them, because the numbers say continuing would be gambling with their life. Now scale up to Mars. The round trip takes about 18 months. Radiation exposure ranges from 300 to 600 millisieverts, depending on solar activity and shielding quality. One Mars mission could use up an entire career allowance. Make the journey, and you can never go to space again. The radiation debt is paid. The biological damage is done. Your cells carry mutations you cannot undo. Your cancer risk is elevated for the rest of your life. For interstellar journeys, the numbers become catastrophic. Even with the best shielding concepts we have, a 10-year mission to another star system would expose crew to thousands of millisieverts, far beyond any career limit, far beyond any level considered safe. The crew would be accepting certain cancer, probable death. They would be volunteering for radiation exposure levels normally seen only in nuclear disasters. Some researchers suggested accepting higher limits for deep space missions. Let astronauts volunteer for missions that exceed safety standards. Let them make an informed choice. The ethics are complicated. Can someone truly consent to a journey that will likely kill them? Can we send people on suicide missions to advance science? Space agencies say no. The limits stand, not because radiation magically becomes safe at 3%, because 3% is where we drew the line. Go beyond it, and we are no longer exploring, we are sacrificing. Radiation exposure is cumulative. Every day in space adds to the total. Every cosmic ray hit increases cancer risk. Every solar particle event pushes the numbers higher. Unlike chemical exposure, which the body can sometimes clear, radiation damage is permanent. The DNA breaks do not heal perfectly. The cell mutations persist. The cancer clock starts ticking and never stops. Studies of astronauts who flew to the moon showed something disturbing. Their cardiovascular disease rates are higher than astronauts who stayed in low Earth orbit. The difference is statistically significant. Something about deep space radiation damages blood vessels, increases plaque formation, accelerates aging of the circulatory system. The effect persists decades after the exposure. Apollo astronauts are still dying from it. Medical technology might improve. Drugs that repair radiation damage. Gene therapies that fix mutations. Treatments that reset cancer risk. All of this is theoretical. None of it exists yet. Betting on future medicine is betting on breakthroughs we cannot guarantee. The limits we have now are based on current reality, current cancer rates, current death statistics. Future improvements are hope. The numbers are facts. Career limits exist because radiation kills. Slowly, invisibly, without mercy. The limits protect astronauts from their own courage. They prevent suicide missions disguised as exploration. They force us to confront an uncomfortable truth. Some destinations are too dangerous to reach. Some journeys are too long to survive. The stars might be one of them. But there is a strange loophole in physics, a way to cheat time itself. Einstein predicted it in 1905. The faster you move, the slower your clock ticks compared to everyone else. Not because your clock is broken, because time itself runs at different rates depending on speed. At normal speeds, the effect is invisible. A jet airplane flying for 10 hours loses a few billionths of a second compared to the ground. Meaningless, unmeasurable without atomic clocks. Approach the speed of light, and the effect becomes dramatic. Travel at 90% light speed, and 1 year on your ship equals 2.3 years on Earth. Get to 99%, and 1 year equals 7 years back home. At 99.9%, 1 year stretches to 22 years. The mathematics are confirmed. Particle accelerators prove it every day. Unstable particles moving at light speed live longer than they should. Time dilation is real. This creates a bizarre opportunity for interstellar travel. If a spacecraft could reach 99% light speed, the crew would age slowly while Earth aged normally. A 40-year journey from the crew's perspective might take hundreds of years from Earth's perspective. The travelers would arrive young. Their grandchildren's grandchildren back home would be long dead. The crew would step onto a new world having barely aged, but they could never go back. Not to the Earth they left. That Earth would be gone. Everyone they knew would be dust. The paradox gets stranger. From the crew's perspective, they are not moving. The destination is moving toward them at 99% light speed. The distances themselves contract. A journey that should take 4.2 years to Proxima Centauri shrinks to 6 months of experience time at high enough speeds. The universe literally becomes smaller when you move fast enough. Space itself changes shape. But achieving these speeds is where the paradox turns cruel. Accelerating to 99% light speed requires energy beyond anything we can generate. The spacecraft's mass increases as it approaches light speed. Not the physical mass, the relativistic mass. The energy needed to accelerate it keeps growing. At 99.9%, the energy approaches infinity. You cannot reach 100%. Physics forbids it. Light speed is a wall you can approach but never touch. Some physicists calculated what it would take to accelerate a small probe to 90% light speed. The energy equals the total output of our star for 1 year. All of it, every photon, every joule, focused on accelerating one small spacecraft. We do not have technology that can harness that energy. We do not have concepts that come close. We can barely harness a fraction of a percent of our star's output. The gap between what we need and what we have is not a gap. It is an impossibility. Time dilation offers a tempting solution to the human lifespan problem. If we could go fast enough, crew members could survive journeys that would normally take centuries. They would age years while the universe aged millennia. They could reach destinations that seem impossible at slower speeds. The physics works, the engineering does not. We cannot build the engines. We cannot generate the power. We cannot overcome the fundamental limitations of propulsion. There is another problem. Relativity is strange. Time dilation works differently depending on your reference frame. From Earth's perspective, the crew barely ages. From the crew's perspective, they age normally, but the destination approaches faster. Neither perspective is wrong. Both are correct. Reality depends on who is measuring it. This is not philosophy. This is confirmed physics. The universe does not have a universal clock. Every observer measures time differently based on their motion. Astronauts on the International Space Station experience tiny amounts of time dilation. They age about 0.007 seconds less than people on the ground after 6 months in orbit. Not enough to notice. Not enough to matter. But it is real. Atomic clocks confirm it. The faster you move, the larger the effect becomes. At relativistic speeds, the difference becomes years, decades, centuries. Time dilation is not science fiction. It is not speculation. It is measured reality. But using it for interstellar travel requires speeds we cannot achieve, propulsion systems we cannot build. energy sources we cannot harness. The universe offers a loophole and then slams the door shut with impossible engineering requirements. We can see the solution. We cannot reach it. And even if we solve propulsion, the nearest star reveals just how far we have to go. 4.24 light-years. That is the distance to Proxima Centauri, our nearest stellar neighbor, a red dwarf star 1/7 the diameter of our own. It has at least 2 planets. One of them orbits in the habitable zone where liquid water could exist. On cosmic scales, Proxima is touching us. On human scales, it might as well be in another universe. Light traveling from Proxima takes 4.24 years to reach Earth. Light moves at 671 million miles per hour. Nothing goes faster. A photon leaving Proxima right now will not arrive until late 2029. That is for something moving at the absolute speed limit of the universe. Now calculate how long it takes humans to make the same journey. The Parker Solar Probe, our fastest spacecraft, travels at 364,000 miles per hour. At that speed, the trip to Proxima would take 7,050 years, 70 centuries, 280 generations. The crew who launched would be forgotten. Their language would have evolved into something unrecognizable. Their descendants might not even remember they are traveling to another star. The mission timescale exceeds all of recorded human history. Engineers proposed faster concepts: nuclear pulse propulsion using atomic bombs for thrust, theoretical top speed around 3% the speed of light. That cuts the journey to 140 years. Still, multiple human lifetimes. Still beyond what current life support systems can sustain. The technology exists on paper. We have never built it. We have never tested it at scale. The costs would exceed the entire global economy. The risks are incalculable. Laser sail systems offer another possibility. A massive laser array built in space, giant reflective sails attached to small probes. The laser pushes the sail, accelerating it to 10% light speed. Journey time drops to 42 years, almost achievable within a human lifetime. The laser array would require infrastructure we do not have. The power demands would drain entire nations. The sail itself would need materials we cannot manufacture yet. But the physics works. This is closer to possible than anything else we have. Breakthrough Starshot is a project pursuing this exact concept. Gram-scale probes, light sails 1 meter across, a ground-based laser array in Chile, target speed 10% of light. Destination Proxima Centauri. The project has funding, real scientists working on real engineering. Launch timeline estimates 20 to 30 years if everything goes perfectly. This is not science fiction. This is actual research happening right now. The probes would be tiny, no crew, no life support, just cameras and sensors. They would fly past Proxima without slowing down. Stopping requires more energy than accelerating. The probes would snap pictures during the flyby, send data back to Earth. The transmission would take 4.2 years to arrive. Scientists would wait 46 years from launch to receive images. Most of the people who started the project would be retired or dead. The commitment spans generations. Scaling this up to carry humans creates impossible problems. A gram-scale probe is easy to accelerate. A 1,000-ton spacecraft carrying crew is not. The laser power requirements increase by 1 trillion times. The sail size becomes absurd, kilometers across. The mass of the ship fights every attempt to accelerate it. You slam back into the rocket equation. More mass requires more energy. More energy requires more infrastructure. More infrastructure requires more money. The costs spiral beyond any economy. Proxima Centauri sits on our doorstep. It is the closest star, the easiest target. If we cannot reach Proxima with current concepts, we cannot reach anything. The galaxy might as well be infinite. Every other star is farther. Every other destination requires more energy, more time, more impossible engineering. Proxima is the test. Proxima is the baseline. We are failing it. The red dwarf will outlive our own star by trillions of years. It will still be burning when the universe is cold and dead. It has time. We do not. Human lifespans are measured in decades. Missions to Proxima are measured in centuries or more. The math does not work. The biology does not align. We are creatures of a single planet trying to reach another star system. The gulf between is not just distance, it is time itself. But some engineers refuse to accept defeat. They propose something radical. Imagine a spacecraft the size of a city, multiple square miles of living space, artificial gravity from rotation, farms growing food under LED lights, water recycling systems running for centuries, a complete self-sustaining ecosystem sealed inside metal walls. This is a generation ship, a vessel designed not for a lifetime but for generations. The crew who launches knows they will never see the destination. Their children will not either. Their great-great-grandchildren might. Project Hyperion studied the concept in detail. A recent design competition drew submissions from teams worldwide. The winning design, called Chrysalis, stretches 36 miles long. It carries 2,400 people. The journey to Proxima would take 250 years at 1.5% light speed. 10 generations of humans born, living, and dying in space. None of them ever setting foot on a planet until arrival. The challenges are staggering. First, you need perfect life support. Water recycling has to be 98% efficient or better. Any loss compounds over centuries. Start with enough water for 2,000 people, and a 2% loss per year means running dry in 50 years. Backup systems need backups. Every component has to be repairable with materials on board. Supply missions are impossible. Help is not coming. Food production faces similar issues. The ship needs farms. Real agriculture in rotating sections with artificial sunlight. The crops have to produce enough calories for the entire population. Waste has to be recycled into fertilizer. The ecosystem has to balance perfectly. One pest invasion, one crop disease, one fungal infection. Any of these could cascade into famine. The ship would become a tomb. Social problems might be worse than technical ones. Studies of isolated groups show predictable patterns. After 500 days, relationships deteriorate, factions form, conflicts escalate. The Mars 500 experiment, conducted on Earth with emergency exits nearby, barely maintained cohesion. Now extend that to 250 years. How do you prevent civil war? How do you maintain order across generations who never chose this mission? The children born aboard did not volunteer. They inherit a prison they cannot escape. Genetic diversity becomes critical. 2,000 people is barely enough to avoid inbreeding over 10 generations. You need careful population management, genetic screening, possibly arranged partnerships to maintain diversity. The ethics are horrifying. You are engineering a society, controlling reproduction, making decisions that would be illegal on Earth. But without these controls, the population collapses into genetic disease and infertility. Education presents another nightmare. Every generation needs to learn skills to maintain the ship: engineering, medicine, agriculture, navigation, computer programming. Knowledge has to transfer perfectly. One generation fails to teach properly, and critical systems start failing. The expertise dies. The ship becomes unfixable. You cannot call tech support. You cannot order replacement parts. The crew has to be self-sufficient in ways no human society ever was. Then there is the psychological weight. Everyone on board knows they are traveling to a destination they will never see. They are living and dying to deliver future generations to a world they cannot experience. What gives their life meaning? What prevents depression and suicide? What keeps them maintaining systems for grandchildren who do not exist yet? These are not engineering problems. These are existential ones. Some designers proposed virtual reality systems, Let crew members experience simulated Earth. Give them the illusion of open spaces. The psychology behind this is uncertain. Does VR help or make things worse? Does it create false memories that make confinement more painful? We do not know. We cannot test this without actually building a generation ship. The stakes are too high to experiment. The ship itself requires propulsion beyond anything we built. Nuclear pulse propulsion is the leading candidate. Detonate atomic bombs behind a massive pusher plate. Ride the shockwave to percent of light speed. The concept works in theory. We tested small-scale versions in the 1960s. Project Orion proved the physics. Scaling it up to a city-sized ship requires thousands of nuclear devices. International treaties ban this. Politics might be the final barrier. Costs are incomprehensible. A generation ship would be the most expensive object ever constructed. Trillions of dollars, decades of construction in space, resources from multiple nations, the political will to fund something that will not show results for centuries. No government has that kind of patience. No economy can sustain it. The project would require global cooperation on a scale we have never achieved. And after all that investment, after building the ship and launching the mission, success is not guaranteed. The ship could fail, systems could break, the crew could die. We would not know for centuries. No communication, no updates, just silence until the mission ends or arrives. The risk is total. The commitment is absolute. One chance to get everything right. But assume we build it. Assume we solve every problem. The human cost is just beginning. 7 people, 14 months, 1 Antarctic research station. By month 6, communication between crew members had reduced to written notes. They stopped speaking. Arguments over minor issues lasted days. Depression became universal. This was not a simulation. This was a real research mission in Antarctica. Help was theoretically available. They still nearly broke. Psychologists study isolation because space agencies need answers. How long can humans endure confinement? What is the breaking point? The data is disturbing. Submarine crews on 90-day missions show increased aggression and anxiety. Prisoners in solitary confinement develop permanent psychological damage in weeks. Astronauts on the International Space Station have 6-month limits, partly because of mental health concerns. Beyond 6 months, the risks increase dramatically. The issue is not just isolation, it is sameness. Every day identical to the last. Same walls, same people, same food, same routine. Human brains need novelty, new experiences, different environments. Take that away, and cognition declines. Depression sets in. Motivation evaporates. Studies show that even watching recorded videos of nature reduces stress in isolated subjects. Imagine decades without ever seeing a tree, a river, a bird, just metal walls and recycled air forever. Social hierarchy creates additional problems. Every group develops power structures. Leaders emerge. Conflicts arise over decision-making authority. In normal societies, people can leave toxic relationships. They can change jobs, move cities, find new friends. On a spacecraft, there is no escape. You are locked in with the same people for years or decades. Personality conflicts become unbearable. There is no divorce, no quitting, no walking away. You are trapped. Research on confined groups shows predictable patterns. After initial bonding, groups split into factions. In-group and out-group thinking intensifies. Small disagreements escalate into permanent rifts. The Mars 500 experiment saw this clearly. Russian and European crew members stopped cooperating. They ate meals separately. They worked independently. The mission barely stayed functional. Adding actual danger and real isolation would make things worse. Sleep disruption compounds psychological stress. Spacecraft do not have day-night cycles like Earth. Crews use artificial lighting to simulate circadian rhythms. Studies show this works imperfectly. Astronauts on the ISS report chronic sleep problems. Sleeping pills become routine. Fatigue builds over months. Decision-making suffers. Reaction times slow. The crew becomes less capable precisely when they need to be sharp. Communication delays with Earth create another psychological burden. Messages to Mars take up to 20 minutes one way. Conversations become impossible. You send a question, wait 40 minutes for a response. The exchange feels artificial, disconnected. Now extend this to light years. A message to a ship near Proxima takes over 4 years to arrive. The response takes another 4 years to return. 8-year conversations. The crew is functionally alone. Earth cannot help with emergencies, cannot provide emotional support, cannot offer advice. The isolation is total. Some psychologists suggested selecting crew members with specific personality traits: low need for social novelty, high tolerance for monotony, introverted tendencies, ability to self-soothe. This creates an ethical problem. Are you selecting astronauts or creating a specialized human type? Are you choosing people or breeding them? The line blurs fast. Selection pressure over generations could change the crew's psychology fundamentally. They might arrive at the destination as a different kind of human. Virtual reality might help but carries risks. Give crew members simulated Earth experiences, and they might prefer the simulation to reality. Addiction to VR becomes a real concern. People could withdraw from actual social interaction and live in digital fantasies. The ship's work still needs doing. Systems need maintenance. If the crew checks out mentally, the mission fails. VR is a tool. It could also become a poison. Medication is another option. Mood stabilizers, anti-anxiety drugs, antidepressants. Keep the crew chemically balanced. The ethics are questionable. Are you treating illness or drugging people into compliance? What happens when the medication runs out? Pharmaceutical supplies do not last centuries. You cannot manufacture complex drugs without Earth's chemical industry. The crew would have to maintain synthesis capabilities, another system to manage, another failure point. The breaking point might not be dramatic. No violent breakdowns, no mutinies, just gradual deterioration. Motivation fades, work becomes sloppy, maintenance is delayed, systems degrade. The ship dies slowly from accumulated neglect. The crew gives up without realizing it. By the time someone notices, recovery is impossible. The mission drifts into failure quietly, predictably, inevitably. But the mind is only part of the problem. The body faces something worse. Every rocket carries a brutal truth in its fuel tanks. The more you weigh, the more fuel you need. The more fuel you carry, the more you weigh. This is the tyranny of the rocket equation, and it destroys almost every spacecraft design before construction even begins. Konstantin Tsiolkovsky discovered this in 1897. The mathematics have not changed. The limits remain absolute. Calculate a simple mission. Launch 1 ton of payload into low Earth orbit. You need roughly 30 tons of rocket at liftoff. The ratio is 30:1. Now extend this to interstellar travel. Launch 1,000 tons toward Proxima Centauri at 1% light speed. The fuel mass becomes astronomical. Millions of tons. Billions. The numbers explode beyond any possibility of construction. Chemical propulsion is hopeless for interstellar missions. Liquid hydrogen and oxygen provide the best performance available. The exhaust velocity is about 4,500 meters per second. To reach 1% of light speed, you need a mass ratio of over 9 trillion to 1. 9 trillion kilograms of fuel for every kilogram of payload, more than the mass of Mount Everest. The spacecraft would collapse under its own gravity before it launched. Nuclear propulsion improves the numbers, but not enough. Fission rockets using uranium fuel can achieve exhaust velocities of 9,000 meters per second, double the chemical performance. The mass ratio drops to about 2 million to 1. Still impossible. 2 million tons of fuel for every ton of spacecraft. The entire rocket becomes a flying fuel tank with a tiny payload compartment. You cannot fit humans in the remaining space. You cannot fit life support. You cannot fit anything. Fusion propulsion offers better theoretical performance. Hydrogen fusion releases enormous energy. Exhaust velocities could reach 30,000 meters per second or higher. The mass ratio improves to about 4,000 to 1, getting closer to possible. But we have never built a working fusion rocket. We have barely sustained fusion reactions for seconds in laboratory conditions. Building a fusion drive that works for decades in space is science fiction. The technology does not exist. The timeline to develop it is unknown. Project Daedalus, designed in the 1970s, proposed a fusion-powered probe to Barnard's star. The design used helium-3 and deuterium fusion. Target speed 12% of light. The spacecraft would weigh 54,000 tons at launch. 50,000 tons of that was fuel. The payload was a tiny fraction. The mission profile assumed mining helium-3 from Jupiter's atmosphere. We have never done this. We do not know if it is practical. The entire concept rests on technologies we cannot demonstrate. Antimatter propulsion is the theoretical best case. Matter and antimatter annihilation converts mass directly to energy. 100% efficiency. Exhaust velocity approaches light speed. Mass ratios drop to manageable levels, 10 to 1, 20 to 1, numbers that look achievable. The problem is making antimatter. Every gram requires phenomenal energy. Current production rates are measured in nanograms per year. We would need tons. The energy cost exceeds our civilization's total power output for centuries. Some engineers proposed gathering fuel during the journey. The Bussard ramjet concept uses magnetic fields to scoop up hydrogen from interstellar space. Use that hydrogen for fusion fuel. The spacecraft never runs out. The mass ratio becomes irrelevant. The idea sounds brilliant until you examine the details. Interstellar space contains about 1 hydrogen atom per cubic centimeter. The scoop would need to be thousands of kilometers across to gather meaningful mass. The drag from the magnetic field might exceed the thrust from the engine. The concept probably does not work. Beam-powered propulsion offers another approach. Build a massive laser array in the solar system. Focus it on a spacecraft's sail. The laser provides thrust without requiring onboard fuel. The mass ratio problem disappears. The spacecraft can be mostly payload. This works in theory. The laser array would cost trillions to build. The sail would need exotic materials to survive the beam's intensity. The targeting has to be perfect across light years. One slight error, and the beam misses. The spacecraft drifts forever. Every propulsion concept hits the same wall. Energy. Moving mass requires energy. Moving it fast requires enormous energy. Moving it to relativistic speeds requires more energy than we can generate. The sun produces about 400 billion watts continuously. We harness less than 1/trillionth of 1% of that. The gap between available and needed is not a gap. It is an ocean we cannot cross. Smaller spacecraft help, but only so much. Reduce payload to 1 ton, and the mass ratio improves. But 1 ton cannot support humans, cannot carry life support, cannot include radiation shielding. You can send probes, you cannot send people. The mission becomes exploration by proxy, valuable but not the same as human presence, not the same as stepping onto another world. Launch costs add another layer of impossibility. Every kilogram lifted from Earth costs thousands of dollars using current rockets. A generation ship weighing millions of tons would cost trillions just to launch. Assembly in space would require hundreds of flights, decades of construction. The logistics overwhelm any budget, any timeline, any realistic planning. The costs are not just high, they are prohibitive. They exceed what human civilization can afford. The fuel mass problem is not an engineering challenge. It is a fundamental limitation of physics. The rocket equation does not care about human ambition. It does not care about our dreams of reaching the stars. It imposes mathematical limits we cannot engineer around. We can improve efficiency. We can develop better fuels. We cannot escape the equation. It is written into the structure of reality itself. But there is one technology that might change everything. 1958. A physicist named Freeman Dyson gathered a team of brilliant minds in San Diego. Their mission was simple and insane: design a spacecraft powered by nuclear explosions. The project name was Orion. The concept was to detonate atomic bombs behind a massive steel plate, ride the shockwave like a surfer on a wave of nuclear fire. The math worked. The physics checked out. They built scale models and tested them with conventional explosives. The models flew. Project Orion's full-scale design was enormous: 4,000 tons at launch, a pusher plate 130 feet across, made of steel and heavy metals. Nuclear pulse units ejected behind the plate at 1-second intervals. Each detonation released energy equivalent to 1 ton of TNT. The shockwave hit the pusher plate. Massive shock absorbers dampened the acceleration. The spacecraft climbed to orbit on a pillar of nuclear fire. The design could reach Mars in 4 weeks, Jupiter in 8 months, Alpha Centauri in 130 years. The engineers were not joking. This was serious research with real funding. They calculated everything down to the number of bombs required, about 800 nuclear devices just to reach orbit, several thousand more for interplanetary missions. Each bomb perfectly timed, perfectly positioned. A failure meant the spacecraft became a dirty bomb, scattering radioactive material across the atmosphere. The environmental concerns killed the project in 1963. The Partial Nuclear Test Ban Treaty banned nuclear explosions in space. Orion died, but the concept never disappeared. Scientists still study it because nuclear propulsion offers the only realistic path to high speeds with current physics. Chemical rockets are too weak. Fusion is not ready. Antimatter is impossible. Nuclear bombs are proven technology. We have thousands of them. We know they work. Using them for propulsion sounds crazy until you examine the alternatives. They are all worse. Modern variants propose using smaller nuclear devices, fission-fusion hybrid pellets instead of full bombs, magnetic fields to direct the blast. The acceleration becomes smoother. The radiation drops. The pusher plate can be lighter. The concept evolves but remains fundamentally the same: controlled nuclear explosions for thrust. The efficiency is remarkable. Exhaust velocities reach 10,000 to 30,000 kilometers per second. Mass ratios become manageable. The spacecraft can carry actual payload instead of being 99% fuel tank. NASA studied nuclear thermal propulsion as a safer alternative. Heat hydrogen using a nuclear reactor. Exhaust the superheated gas for thrust. No explosions. No radioactive debris. The reactor runs continuously like a car engine. The concept is proven. The Nerva program in the 1960s built and tested working engines. They achieved exhaust velocities, double chemical rockets. Budget cuts killed the program before flight testing. The technology exists. We chose not to use it. Nuclear electric propulsion is another option. Use a reactor to generate electricity. Power ion engines with the electricity. Ion engines are incredibly efficient. They produce tiny thrust continuously for years. The acceleration is gentle, 1,000th of Earth's gravity or less, but they never stop. Month after month, year after year, the spacecraft gradually accelerates to high speeds. Journey time to Mars drops from 7 months to 3, to the outer solar system in years instead of decades. The problem with all nuclear propulsion is public perception. The word nuclear triggers fear. Images of Chernobyl, Fukushima, Hiroshima, nuclear rockets sound like weapons. Launch accidents become nuclear disasters. A rocket exploding during liftoff scatters radioactive material across the landscape. The risk is real. The consequences are severe. No government wants to be responsible for that. No space agency wants that liability. Assembly in orbit solves the launch problem partially. Build the nuclear systems in space. Never bring them near Earth's surface. Launch accidents do not scatter radiation. The reactor activates only in deep space far from any planet. This is safer, but harder. Orbital construction is expensive, difficult. Every component needs launching separately. Assembly requires dozens of spacewalks, robotic systems, years of work. The complexity increases costs dramatically. Radiation shielding adds more mass. Nuclear reactors emit gamma rays and neutrons. The crew needs protection. Water works as good shielding. Surround the living quarters with water tanks, meters of thickness. Tons of mass. The spacecraft grows heavier. The mass ratio worsens. You gain efficiency from nuclear propulsion and lose it to shielding requirements. The balance is delicate. Fuel longevity is an advantage. Nuclear fuel stores incredible energy density. Uranium or plutonium pellets smaller than your fist contain energy equivalent to tons of chemical fuel. A few hundred kilograms of nuclear fuel could power a spacecraft for decades. No refueling, no resupply. The reactor runs until the fuel depletes or the mission ends. Chemical rockets burn their fuel in minutes. Nuclear systems burn for years. The difference is revolutionary, but nuclear technology has political baggage. International treaties restrict nuclear materials in space. Weapon proliferation concerns. National security issues. Space agencies need permission to fly nuclear systems. Permission requires environmental reviews, safety assessments, public hearings. The bureaucracy is enormous. Timeline delays stretch missions by years. Projects die in paperwork before construction begins. The technical challenges are solvable. The physics works. The engineering is understood. The barriers are not physical. They are political and social. We could build nuclear-powered spacecraft today with existing knowledge. We choose not to. Fear outweighs ambition. Caution outweighs exploration. The technology exists. The will does not. And even with nuclear propulsion, there is something that changes the game completely. Imagine a sail 1,000 feet across, thinner than plastic wrap, made of materials that reflect 99.9% of light, weigh almost nothing. This is a light sail, and scientists believe it could reach another star system in decades, not centuries, not millennia, decades. The physics is simple. Light carries momentum. Photons hit the sail and push it. The push is tiny, but it never stops. Sunlight is free. The sail needs no fuel. It accelerates continuously. In orbit, light sails using sunlight achieve modest speeds. The pressure from our star is weak this far out. A sail needs to be enormous to catch meaningful thrust. But the concept works. Japan's Ikaros probe deployed a light sail in 2010. It successfully demonstrated solar sailing between Earth and Venus. The technology is proven. The question is how to scale it up. Breakthrough Starshot proposed the answer. Do not use sunlight, use lasers. Build a ground-based laser array in the Chilean desert, 100 million watts of focused light. Aim it at a tiny probe with a meter-wide sail. The laser accelerates the probe to 10% of light speed in minutes. The probe weighs 1 gram. The sail is impossibly thin. The acceleration is violent. 100,000 times Earth's gravity. Nothing mechanical survives that except a simple chip. Cameras. Minimal electronics. No moving parts. The numbers are stunning. 10% light speed means reaching Proxima Centauri in 42 years. The probe flies past without slowing. Stopping requires more energy than accelerating. Cameras snap pictures during the flyby. Data streams back to Earth. The transmission takes 4.2 years to arrive. Total mission time from launch to data reception is 46 years. 1 human lifetime. Scientists who start the project could see the results before dying. The laser array is the real challenge. 100 gigawatts of continuous power focused into a beam miles across. The array would cover several square miles of desert. Thousands of individual lasers working in perfect synchronization. Adaptive optics to correct for atmospheric distortion. The technology exists in principle. The scale is unprecedented. The cost is estimated at $5 to $10 billion. Expensive but achievable, comparable to a large particle accelerator or space telescope. Targeting is critical. The probe accelerates for minutes. The laser has to track it perfectly. Any deviation and the beam misses. The probe tumbles out of control. The mission fails. The tracking system needs precision beyond anything attempted before. Computer control with real-time atmospheric correction. Artificial intelligence handling targeting decisions at millisecond intervals. The software alone is a breakthrough project. The sail material is exotic. Reflectivity has to be nearly perfect. Any absorbed light vaporizes the sail instantly. The laser delivers gigawatts per square meter. Regular materials would explode. Scientists proposed graphene or exotic metamaterials, structures engineered at the atomic level. Manufacturing these at scale is not currently possible. Research continues. Progress is slow but steady. Multiple probes improve success odds. Launch thousands of gram-scale probes. Some fail during acceleration. Some drift off course. Some encounter micrometeorites during the journey. But if 10% reach Proxima, the mission succeeds. Redundancy through numbers. The cost per probe is low. The laser is the expensive part. Once built, it can launch probes regularly. 1 per week. 100 per year. A fleet heading to different stars. Communication uses the sail as a receiver. The probe has no power for a transmitter. Instead, it modulates reflectivity on the sail, creates patterns in reflected light. Earth-based telescopes detect the patterns. The bandwidth is minimal, enough for images. Basic telemetry, no video, no real-time data, just snapshots and status updates. Better than nothing, better than waiting centuries. The flyby limitation is frustrating. The probe cannot stop, cannot orbit, cannot land. It races past at 10% light speed. Everything happens in minutes, hours at most. The cameras have one chance to capture images. After that, the probe continues into deep space. Forever, it becomes another piece of human-made debris drifting through the galaxy. A message in a bottle that will outlive our civilization. Scaling this up to carry humans is impossible with current concepts. A 1,000-ton spacecraft needs a laser array the size of a continent. Power requirements exceed global energy production. The sail becomes impractical at large scales. Lasers for tiny probes work. Lasers for crude ships do not. The physics does not scale favorably. Light sails are for exploration, not colonization, not human transport. Some physicists proposed particle beams instead of lasers. Accelerate electrons to near light speed. Aim the beam at the spacecraft. Electrons carry more momentum per photon than light. The push is stronger. The spacecraft accelerates faster. Theoretical speeds reach 20% of light. Journey time to Proxima drops to 21 years. The technology is more speculative. Particle accelerators are well understood. Particle beam propulsion is not. The concept exists on paper. Reality is unclear. Breakthrough Starshot represents the best near-term hope for interstellar exploration, not human missions, not colonization, but scientific reconnaissance. Cameras reaching another star within a human generation, data streaming back across light years, proof that we can touch another solar system. The psychological impact would be enormous. The scientific value is immeasurable. The first images of an exoplanet surface, the first measurements of another star's environment, the first confirmation that interstellar travel is possible. And if we build that technology, we face one final reality about time. Physics imposes a speed limit. Nothing moves faster than light. 300 million meters per second, 671 million miles per hour. This is not an engineering constraint. This is fundamental to how the universe works. Photons travel at light speed. Everything with mass travels slower. The gap between slower and light speed requires infinite energy to close. You can approach light speed. You can never reach it. Proxima Centauri sits 4.24 light-years away. A light-year is the distance light travels in 1 year, 9.5 trillion kilometers, nearly 6 trillion miles. Multiply by 4.24, and you get 25 trillion miles to our nearest stellar neighbor. At light speed, the journey takes 4.24 years. This is the absolute minimum time, the floor, the fastest possible trip even in theory. Now add acceleration time. Spacecraft do not start at light speed. They accelerate gradually, even with perfect propulsion. Accelerating to 90% light speed takes time. If you could sustain one gravity of acceleration continuously, you would reach 90% light speed in about 9 months. Then you coast. Then you decelerate for another 9 months at the destination. Total trip time around 6 years. Still faster than any realistic technology. Still impossible with current propulsion. Breakthrough Starshot aims for 10% light speed with laser-pushed probes. That reduces the floor time to 42 years. The probe does not slow down, flies past at full speed. Total mission duration is 46 years, including communication lag. This assumes everything works perfectly. The laser performs flawlessly. The probe survives acceleration. Targeting is exact. Nothing breaks during the journey. The success rate for first attempts is historically low. Expect failures, expect delays, expect the timeline to extend. Human missions face additional constraints. People need life support, air, water, food, radiation shielding, medical facilities, living space. All of this adds mass. Mass reduces achievable speed. The propulsion system scales up. The fuel requirements explode. Journey times extend beyond the probe estimates. Even with breakthrough propulsion, a crewed mission to Proxima probably takes at least 100 years, multiple human lifetimes. Generation ships or suspended animation, no quick trips, no weekend voyages. The 40-year minimum applies only if we achieve near-light speeds. Current spacecraft technology is nowhere close. Voyager 1 travels at 38,000 miles per hour. That is 0.006% of light speed. At that velocity, reaching Proxima takes 73,000 years. Faster than Voyager, but still, chemical propulsion gets you to maybe 0.1% light speed. 7,000-year journey. Nuclear pulse propulsion reaches 1 to 3% light speed. 140 to 420 years. Still multiple generations. Time dilation helps only at relativistic speeds. Below 50% light speed, the effects are minimal. At 10% light speed, time dilation factor is just 1.005. The crew ages normally. Earth ages normally. No shortcuts, no cheats. The journey takes the time it takes. At 90% light speed, the factor jumps to 2.3. 1 year on the ship equals 2.3 years on Earth. Noticeable but not revolutionary. You still age decades during the journey. Cryogenic suspension might allow crews to skip the journey time subjectively, freeze them shortly after launch, thaw them before arrival. The technology does not exist yet. Freezing damages cells. Ice crystals destroy tissue. Current cryonics research focuses on preservation after death, not revival. Freezing living humans without killing them is science fiction. Research continues, but breakthroughs are not guaranteed. We cannot plan missions around technology that does not exist. Hibernation is more realistic. Bears do it naturally. Lower metabolism, reduce food and water needs, sleep through most of the journey. Studies show promise. Modified hibernation could extend food supplies dramatically, reduce psychological stress from confinement. The crew spends months or years unconscious. They age slowly. Resources last longer. But hibernation is not freezing. Metabolism continues. Aging continues. A 40-year journey still takes 40 years of biological time, just most of it asleep. The 40-year minimum for Proxima is aspirational. It assumes technology we barely have concepts for. Laser arrays not yet built, propulsion systems not yet tested, materials not yet manufactured, success rates not yet proven. Realistic timelines are longer, much longer. First missions will be slower, conservative, proven technology only. That means journey times measured in centuries, not decades. The minimum is theoretical. The reality is harsher, and Proxima is the closest star. Every other destination is farther. Barnard's star is 6 light-years away. Sirius is 8.6. Wolf 359 is 7.9. The nearby stars cluster within 10 to 20 light-years. Even at 10% light speed, these journeys take 100 to 200 years. The galaxy is enormous. The stars are spread across 100,000 light-year diameters. We can barely conceive of reaching our nearest neighbors. The rest might as well be unreachable. Time is the ultimate barrier. Not energy, not propulsion, not radiation. Time. Human lifespans are finite. Missions exceeding human lifetimes require generation ships or suspension technologies we do not have. The 40-year minimum mocks our ambitions. Even achieving it is beyond current capabilities. We dream of stars. Physics dreams of nothing. The gap between is measured in years we do not have. But how far have we actually gone? September 5th, 1977. A Titan rocket lifted off from Cape Canaveral, carrying a spacecraft the size of a small car. Voyager 1. Mission duration: 5 years to study Jupiter and Saturn, then continue into deep space, forever. The spacecraft carried cameras, particle detectors, magnetometers, a golden record with sounds and images of Earth, a message to any intelligence that might find it billions of years from now. Voyager 1 is still transmitting. 47 years after launch, the signal is weak, 20 watts, less power than a refrigerator light bulb. The radio waves take 22 hours to reach Earth, traveling at light speed. NASA listens with massive antennas. The data comes through: temperature readings, cosmic ray counts, magnetic field measurements. The spacecraft is alive and sending information from beyond the solar system. Current distance: 14.8 billion miles from Earth, 157 astronomical units. An astronomical unit is the distance from Earth to our star, roughly 93 million miles. Voyager crossed the heliopause in 2012, the boundary where solar wind stops. Interstellar space begins. The spacecraft entered territory no human-made object ever reached before. It is still barely outside our cosmic doorstep. The nearest star is Proxima Centauri, 25 trillion miles away. Voyager has traveled 14.8 billion miles in 47 years. That is 0.06% of the distance to Proxima. At current speed, Voyager would take 73,000 years to reach our nearest stellar neighbor. If it were aimed at Proxima, which it is not, Voyager is headed toward a star called AC plus 79 degrees 3888. It will pass within 1.6 light-years of that star in about 40,000 years, 40 millennia, 800 generations. The spacecraft will outlast human civilization. The electronics will fail eventually. The power supply is a radioisotope thermoelectric generator. Plutonium-238 decays and produces heat. Thermocouples convert heat to electricity. The plutonium has a half-life of 87 years. Power output drops annually. NASA started shutting down instruments in 2019 to conserve power. The cameras are off. Heaters are off. Only essential systems remain active. By 2030, power will be too low to run any instruments. Voyager goes silent but continues moving. The structure is more durable. Aluminum and titanium frame, gold-plated copper electronics, the golden record protected by an aluminum cover. Cosmic rays degrade materials slowly. Micrometeorites erode surfaces. Over millions of years, the spacecraft will become unrecognizable, eventually just debris, a cloud of particles drifting through space. But for now, it is intact, a functioning machine in the void. Voyager's speed is 38,000 miles per hour relative to our star. That is 17 kilometers per second. Sounds fast. It is nothing on cosmic scales. Light travels 186,000 miles per second. Voyager travels 0.006% of light speed. The comparison is humbling. Our fastest machine is pathetically slow. A snail crossing a continent. The distances are incomprehensible. 2 identical spacecraft were launched. Voyager 2 left 16 days before Voyager 1. Different trajectory, different targets. Voyager 2 visited Uranus and Neptune, the only spacecraft ever to reach those planets. Now both Voyagers are in interstellar space. Voyager 2 is about 12 billion miles from Earth, slightly behind its twin, both heading in different directions into the galaxy, both carrying their golden records, both silent ambassadors of a species that might be extinct before they reach anything. The power supply dictates mission end. Without electricity, the spacecraft cannot transmit, cannot point antennas at Earth, cannot operate instruments. The hardware will function mechanically. Attitude control uses no power. Momentum wheels keep the spacecraft stable, but without communication, Voyager becomes lost. We cannot track it, cannot receive data. It becomes another piece of space junk wandering the galaxy, forgotten, invisible. Voyager represents our maximum reach with current technology. 47 years of travel, 14 billion miles, 0.06% of the distance to the nearest star. The spacecraft proves we can build machines that function for decades in space. We can send signals across billions of miles. We can explore the outer solar system. We cannot reach the stars. The gap is too vast, the speed too slow, the time too long. Future spacecraft might go faster. Nuclear propulsion could multiply Voyager's speed by 10 or 20 times, cut the journey to Proxima to 3,000 or 4,000 years. Still hopeless for human missions. Still multiple generations. Still beyond practical planning. Voyager defines our current limit. It is a limit measured in fractions of the distance we need to travel. But there is a boundary to everything we can ever touch. The Milky Way galaxy is not alone. It is part of a cluster. 54 galaxies bound together by gravity. Andromeda is the largest, 2.5 million light-years away. Moving toward us at 70 miles per second, the Milky Way and Andromeda will collide in 4 billion years, merge into one enormous elliptical galaxy. Triangulum is the third major member. 30 other dwarf galaxies orbit the 3 giants. This is the local group, our cosmic neighborhood, our gravitationally bound family. Beyond the local group, space is expanding. Galaxies are moving apart, not because they are flying through space, because space itself is growing. The fabric of the universe stretches, carries galaxies with it. The farther away a galaxy is, the faster it recedes. This is Hubble's law, discovered in 1929, confirmed by decades of observations. The universe is expanding, and the expansion is accelerating. Dark energy drives this acceleration. We do not know what dark energy is. We cannot detect it directly. We only see its effects. Galaxies far enough away are receding faster than light, not moving through space faster than light. That would violate relativity. But space between us and them is expanding faster than light can cross it. The light they emit will never reach us. They are beyond what scientists call the cosmological event horizon. Calculate where this horizon sits. About 18 billion light-years from Earth. Everything beyond that distance is receding faster than light. We can see some of these galaxies because their light was emitted when they were closer. The light has been traveling for billions of years. The galaxies have since receded beyond the horizon. We see their past. We will never see their future, never reach them, never communicate with them. They are effectively removed from the universe we can interact with. The local group is well within this horizon, 18 million light-years in radius. The group is much smaller, about 10 million light-years across. We are gravitationally bound. Gravity is stronger than expansion at these scales. The group will not expand, will not drift apart. Future civilizations, billions of years from now, will still have the local group to explore. Everything else will have vanished beyond the horizon. This creates a hard limit on human expansion. Even if we developed perfect propulsion, even if we reached light speed somehow, we can only ever reach the local group. That is the maximum possible exploration zone. 18 million light-years. Sounds vast. It represents about 6% of the observable universe. 94% of the galaxies we can see are already unreachable. Space is expanding too fast. The distance grows too quickly. Physics forbids contact. Within the local group, there are billions of stars, trillions of planets, enough worlds to explore for millions of years. The limitation is not targets, it is time and distance. Andromeda is 2.5 million light-years away. At light speed, the journey takes 2.5 million years. No human civilization lasts that long. No species remains unchanged across such timescales. Any mission to Andromeda would arrive to find whatever launched it extinct on the homeworld. Evolution would have moved on. The travelers would be the last of their kind. Even reaching nearby galaxies in the local group is effectively impossible. The Small Magellanic Cloud is 190,000 light-years away. Large Magellanic Cloud is 160,000. Both are satellite galaxies of the Milky Way. Visible from the southern hemisphere, beautiful spiral structures, unreachable in practice. Journey time exceeds the entire existence of modern humans. Homo sapiens has existed for 300,000 years. A trip to the Magellanic Clouds would take more than half that long. One way, at light speed, which we cannot achieve. The cosmological horizon will shrink over time. Dark energy continues accelerating expansion. Distant galaxy groups recede faster, eventually cross the horizon, disappear from view. Billions of years from now, only the local group will remain visible. The rest of the universe will have redshifted into invisibility. Future astronomers will see a small cluster of galaxies surrounded by empty darkness. They will not know about the billions of galaxies that once were visible. Evidence of the larger universe will be gone, erased by expansion. This is the ultimate prison. We are confined to the local group by fundamental physics. Cannot engineer our way out. Cannot develop technology fast enough. Cannot cheat the expansion of space. The universe itself limits how far we can go. Draw a sphere 18 million light-years in radius around Earth. Everything inside is theoretically reachable. Everything outside is not, forever. The boundary is absolute, final, written into the mathematics of space-time. 6% of the observable universe. That is our maximum playground. Sounds generous. It is incomprehensibly small compared to what exists beyond. Hundreds of billions of galaxies. Trillions of stars. Uncountable planets. All of them unreachable. All of them might as well not exist for the purposes of human exploration. We can see them through telescopes, study their light, measure their properties. We can never visit, never contact, never interact. The local group boundary is not a technical limit. It is a cosmic one. Physics drew the line. Expansion holds it in place. Nothing we invent will change it. Imagine a wall you cannot see, cannot touch, cannot cross. It exists not in space, but in the structure of space-time itself. This is the cosmological event horizon, the ultimate boundary of everything humanity can ever influence or reach. Physics places it roughly 16 billion light-years from Earth right now. Beyond that line, we are cut off from the universe forever. The horizon works differently than you might think. It is not a physical barrier. Spacecraft do not bounce off it. Instead, space expands faster than light can cross it. Send a signal toward a galaxy beyond the horizon, and the signal travels at light speed. But the space between grows faster. The distance increases. The signal never gets closer. It runs on a cosmic treadmill that accelerates away faster than the signal can approach. Eventually, the signal redshifts into nothingness, diluted, stretched, lost. This horizon is shrinking. Every second, more of the universe crosses the boundary and becomes unreachable. Galaxies visible today will vanish beyond the horizon over billions of years. The observable universe appears to grow as light from distant regions reaches us for the first time, but the reachable universe shrinks constantly. Dark energy drives the acceleration. The expansion rate increases. The horizon moves closer. We lose access to more and more of reality. Calculate what this means for exploration. A spacecraft launched today toward a galaxy 15 billion light-years away would never arrive. Even traveling at light speed, the expansion carries the destination away faster than the ship approaches. The journey becomes infinite. The fuel runs out. The crew dies. The spacecraft drifts forever in expanding space, never reaching anything. The mission fails not from mechanical breakdown, but from fundamental physics. Scientists confirmed this through observations of distant supernovas. Type Ia supernovas have consistent brightness. They work as standard candles for measuring cosmic distances. Astronomers measured hundreds of these explosions in distant galaxies, plotted distance versus redshift. The data revealed acceleration. The universe is not just expanding, the expansion is speeding up. The rate increases over time. This discovery won the Nobel Prize in 2011. The implications are profound and disturbing. The horizon's position depends on the exact values of cosmological constants: dark energy density, Hubble parameter, matter density. Scientists measure these values through observations, but uncertainties remain. The horizon might be slightly closer or farther than current estimates. The margin of error is billions of light-years. Sounds huge. Makes no practical difference. Whether the horizon is 14 or 18 billion light-years away, it is unreachable either way. The precision matters for cosmology, not for exploration. Some physicists speculated about changing the horizon's position, manipulate dark energy, alter the expansion rate, create bubbles of modified spacetime where different rules apply. All of this is science fiction. We do not understand dark energy well enough to manipulate it. We cannot even detect it directly, only measure its effects indirectly through expansion rates. Controlling something we cannot detect or understand is impossible. The speculation is entertaining. The reality is fixed. The horizon applies to information too. Light from beyond the horizon never reaches us. Information cannot travel faster than light. Everything beyond the boundary is permanently unknowable. We cannot see what is happening there, cannot measure it, cannot study it, cannot verify it exists at all. For practical purposes, the universe beyond the horizon does not exist. We are confined to what we can observe, what we can theoretically reach. The rest is forever hidden. Future civilizations will face a bleaker universe. In trillions of years, only gravitationally bound local structures will remain visible. Individual galaxy groups. Everything else will have vanished beyond the horizon. Astronomers in that era will see a small cluster of galaxies surrounded by empty blackness. No cosmic microwave background, no distant galaxies, No evidence that a larger universe ever existed. They will never know what we know now. The expansion will have erased the evidence. The cosmological event horizon is the final word on how far humans can explore, not how far we will go with current technology, how far we can possibly go with any technology allowed by physics. The boundary is absolute, unchangeable. We are trapped inside it as surely as we are trapped inside time itself. The universe beyond continues to exist. We are permanently separated from it. The wall is invisible. The wall is real. The wall is forever. But something is making that wall close in faster. 1998. Two teams of astronomers studying distant supernovas reached the same shocking conclusion. The universe is not just expanding. The expansion is accelerating. Galaxies are flying apart faster now than they were billions of years ago. Something is pushing them. Something invisible. Something that makes up 70% of the universe's energy density. Scientists named it dark energy without understanding what it is. The discovery overturned expectations. Gravity pulls things together. The Big Bang pushed things apart. Astronomers expected expansion to slow over time as gravity fought back, like throwing a ball upward. Gravity slows it. Eventually, it stops and falls. The universe should work the same way. Expansion slows, maybe stops, maybe reverses into a big crunch. The data showed the opposite. Expansion is speeding up. The ball is accelerating upward. Something is fighting gravity and winning. Measure the acceleration rate through redshift observations. Light from distant galaxies stretches as space expands. The stretching shifts wavelengths toward red. More redshift means more expansion. Plot redshift versus distance for thousands of galaxies. The curve reveals acceleration. The slope increases at greater distances. Earlier epochs. The expansion rate was slower billions of years ago. It increased over time, currently accelerating at an exponential rate that will continue forever unless something changes. Dark energy behaves strangely. Unlike matter or radiation, it does not dilute as space expands. Matter spreads thinner as volume increases. Dark energy density stays constant. More space means more total dark energy. The amount increases. This positive feedback drives runaway acceleration. The more space expands, the more dark energy appears. The more dark energy, the faster the expansion. The cycle amplifies itself. No natural braking mechanism exists. Calculate the future. In 100 billion years, all galaxies outside the local group will have vanished beyond the cosmological horizon. Their light stretched to infinite wavelengths, effectively invisible. The sky will be empty except for merged remnants of the Milky Way and Andromeda. Dark, isolated. Future civilizations will see no evidence of a larger universe. They will think they inhabit a small island of matter, surrounded by infinite nothing. They will be right. Everything else will have accelerated away. Some models predict even more dramatic endings. If dark energy strengthens over time, acceleration could become extreme. The Big Rip scenario. Expansion accelerates until it tears apart galaxy clusters, then galaxies, then solar systems, then planets, eventually atoms themselves. The universe rips apart at every scale. Timescale for this is tens of billions of years, maybe never. The uncertainty is enormous. We do not understand dark energy well enough to predict its future behavior. Other models suggest dark energy could weaken. Expansion might slow after all, maybe reverse. The data so far shows constant density, no evolution over cosmic time. But we have only measured the recent universe, the last few billion years. Dark energy might change on longer timescales. We cannot rule it out, cannot confirm it. The observations are insufficient. The uncertainty persists. The cosmological constant is one explanation. Einstein's biggest blunder, he called it. He added a term to his equations to keep the universe static. Then Hubble discovered expansion. Einstein removed the term. Turns out it might have been right all along. The cosmological constant represents energy inherent to empty space itself, vacuum energy, quantum fluctuations. It never changes, never dilutes, perfectly explains current observations. We do not understand why it has the value it does. The measured value is 120 orders of magnitude smaller than theoretical predictions. This is the worst prediction in physics history. Alternative theories propose modified gravity. Maybe general relativity is wrong at cosmic scales. New terms in the equations create apparent acceleration without dark energy. The math works. The physics is speculative. No experimental evidence supports modified gravity over dark energy. Occam's razor favors the simpler explanation. Unknown energy is simpler than rewriting gravity. Strange but true. Acceleration changes everything about long-term exploration. Without it, distant galaxies would remain reachable given enough time. With acceleration, they cross the horizon and become permanently inaccessible. The reachable universe shrinks, will continue shrinking. Nothing we do changes this. Technology cannot fight the expansion of space. Speed improvements mean nothing when the destination is receding faster than light. We are losing access to most of the cosmos in real time. The implications are philosophical and scientific. We live in a brief cosmic moment when distant galaxies are still visible. Future eras will have less to observe. Past eras had different expansion rates. Different physics dominated different epochs. We are lucky to exist when we can still see evidence of the Big Bang, the cosmic microwave background, distant quasars, ancient galaxies. This window is closing. Slowly but inevitably, the universe is hiding itself from us, one galaxy at a time. And the force doing this is something we barely comprehend. 70% of the universe is something we cannot see, cannot measure directly, and do not understand. Dark energy. The name describes our ignorance more than the phenomenon itself. We detect its effects through expansion rates, through gravitational lensing, through structure formation, but we have no idea what it actually is. No particles, no fields, no mechanism, just observations that something is pushing the universe apart. The simplest explanation is vacuum energy. Empty space is not truly empty. Quantum mechanics predicts that virtual particles pop in and out of existence everywhere. Particle-antiparticle pairs blink into reality for fractions of a second and annihilate. This creates energy even in perfect vacuum. Calculate the expected vacuum energy density using quantum field theory. The answer is 10 to the power of 120 times larger than what we measure. This is not close. This is catastrophically wrong. The worst prediction in physics. Scientists call this the cosmological constant problem. Why is vacuum energy so small compared to predictions? Nobody knows. Maybe most of it cancels out through unknown mechanisms. Maybe quantum gravity changes the calculation. Maybe our entire framework is wrong. Decades of research have produced no answers, just more questions. The gap between theory and observation mocks our understanding. We are missing something fundamental about how the universe works. Alternative theories propose evolving dark energy, not a constant but a field that changes over time. Quintessence, phantom energy, various mathematical formulations with different properties. Some predict dark energy will weaken, some predict strengthening, some predict it might even reverse. Observations so far show no evolution. Dark energy looks constant across billions of years. But the measurements have limited precision. Subtle changes could be hiding in the error bars. Modified gravity offers another approach. Maybe general relativity breaks down at cosmic scales. Einstein's equations need extra terms that become important over billions of light years. These modifications could mimic dark energy without requiring unknown energy. The math is complex. The physics is uncertain. No experimental evidence supports this over standard cosmology. The idea remains speculative, interesting but unproven. Some physicists wondered if dark energy is real at all. Maybe we are misinterpreting the data, systematic errors in measurements, selection bias in supernova samples, incorrect distance estimates. The cosmology community investigated these possibilities thoroughly. The acceleration is confirmed by multiple independent methods: Type Ia supernovas, cosmic microwave background measurements, baryon acoustic oscillations, large-scale structure surveys. All point to the same conclusion: dark energy is real. The effect is not an error. The energy density is mind-boggling when you calculate the total. Dark energy makes up 70% of all energy in the universe. Dark matter is 25%. Normal matter is just 5%. Everything we can see and touch, all the stars, all the galaxies, all the planets, all the gas and dust, 5%. We live in a universe dominated by things we do not understand. Dark matter, dark energy. Our ignorance outweighs our knowledge 14-1. Experiments to detect dark energy directly have failed. It does not interact with normal matter except through gravity. No electromagnetic force, no nuclear force, no way to trap it, no way to measure it in a laboratory. Unlike dark matter, which might be particles we could detect someday, dark energy seems to be a property of space itself. You cannot bottle space, cannot experiment on it in controlled conditions, cannot isolate its effects from the whole universe. The mystery has profound implications for the fate of everything. If dark energy density increases, the Big Rip becomes possible. Space expands so fast, it tears apart atoms. If density decreases, expansion might slow or reverse. The Big Crunch, everything collapses back together. If density remains constant, we get the Big Freeze. Eternal expansion, heat death, stars burn out, black holes evaporate. The universe becomes cold, empty, dead. All three scenarios end in obliteration, just different timescales and mechanisms. Current best estimates suggest the Big Freeze, constant dark energy, eternal acceleration. The expansion never stops, never slows. Galaxies drift apart. Star formation ceases as gas disperses. Existing stars age and die. No new ones form. Trillions of years from now, the universe will be dark, except for occasional flashes from black holes evaporating through Hawking radiation. Then even those die. Pure emptiness remains, expanding forever, getting colder, getting darker, until temperature approaches absolute zero, until distances approach infinity. The ultimate fate of everything. Dark energy determines this future. We do not know what it is, cannot control it, cannot predict its evolution. The universe's destiny is written in something we barely detected and do not understand at all. This is where physics stands today, observing effects, measuring expansion, building models. But the fundamental nature of 70% of reality remains completely mysterious. We are children trying to understand forces beyond our comprehension. The universe is teaching us humility. The lesson is brutal and clear. And when you add up what this means for exploration, the numbers become crushing. Calculate the total volume of the observable universe. 93 billion light-years in diameter, roughly 4 times 10 to the power 80 cubic light-years. Hundreds of billions of galaxies, each containing hundreds of billions of stars, trillions of planets. The numbers are incomprehensible. Now calculate how much of that we can ever reach. The cosmological event horizon sits about 16 to 18 billion light-years away. Everything beyond that is receding faster than light, unreachable even in theory, but the reachable zone is much smaller. Gravitationally bound structures resist expansion. The local group remains accessible, 18 million light-years across. Everything beyond our local cluster is accelerating away, eventually crosses the horizon, disappears forever. Do the math. The local group's volume is a tiny fraction of the observable universe's volume, roughly 6%. 6. We can see the other 94% through telescopes. We can never visit it. Never send signals to it. Never interact with it in any way. Physics forbids contact. Space expands too fast. The gap grows too quickly. We are trapped in our cosmic neighborhood while watching the rest of the universe accelerate away into darkness. That 6% contains about 50 galaxies. The Milky Way, Andromeda, Triangulum, dozens of dwarf galaxies. Total star count is around 1 trillion. 1 trillion stars across all the galaxies in the local group. Sounds like plenty until you compare it to the universe. The observable universe contains about 200 billion galaxies. 100 billion trillion stars total. We have access to 0.00001% of all stars. 1 in 10 billion. The rest are gone, unreachable, lost to expansion. Even that 6% is mostly inaccessible practically. Light speed travel to Andromeda takes 2.5 million years. No technology we can imagine sustains a mission that long. No biological organism remains unchanged across such timescales. Evolution operates faster than that. The crew that arrives would be a different species than the crew that launched, assuming they survive at all, assuming the mission does not fail, assuming technology lasts millions of years without maintenance or replacement parts. Focus on what is truly reachable with any plausible technology. Our galaxy, the Milky Way, 100 billion stars, 400 billion planets estimated. Huge numbers, tiny compared to the universe. The Milky Way is 100,000 light-years across. Even traveling at 10% light speed, crossing the galaxy takes 1 million years. The far side might as well not exist for human exploration. Too far, too slow, too long. Narrow it further to what is reachable within human timescales. Assume 10% light speed. Assume journeys under 1,000 years are acceptable for generation ships. Draw a sphere 100 light-years in radius around Earth. Everything inside is theoretically explorable. Everything outside requires missions longer than civilizations last. The sphere contains about 14,000 stars, 14,000 out of 100 billion trillion in the observable universe. We have access to 0.000000014%, 1 in 7 trillion. Most of those 14,000 stars are dim red dwarfs, hostile environments, planets tidally locked, one side eternally day, one side eternally night, extreme temperature differences, volatile atmospheres, not ideal for colonization. Maybe 50 to 100 stars in our local sphere are similar to our own. Yellow main sequence stars with potentially habitable worlds. 50 candidates. That is the entire roster of practical destinations. 50 stars out of billions of trillions. The 6% reality is actually a 0.0000001% reality. We can see nearly everything. We can reach almost nothing. The universe is showing us a buffet and serving us crumbs. We peer through telescopes at galaxies 13 billion light-years away. Beautiful spiral structures, dense star clusters, exotic phenomena, all of it forever beyond reach. We are cosmic tourists, looking through a window we can never open. The view is spectacular, the access is non-existent. Some optimists argue 6% is enough. 1 trillion stars give plenty to explore, enough to keep humanity busy for millions of years. True in theory, false in practice. The distances are too vast, the speeds too slow, the time too long. Even exploring our local neighborhood of 50 stars would take thousands of years. Exploring the local group would take billions. By then, we would have evolved into something unrecognizable, if we survived at all. The harsh truth is that we can see the universe, but cannot touch it. Our eyes outreach our hands by billions of light years. We developed astronomy before astronautics. We can measure the cosmos before we can travel it. The gap between observation and exploration is not closing, it is widening. Telescopes improve faster than propulsion systems. We see more and more of what we can never visit. The universe keeps revealing itself while simultaneously running away. 6% is the generous estimate. The realistic number is closer to 0.01%. The practical number is even smaller. We are confined to a bubble so small compared to the cosmos that calling it a prison is generous. It is a cell, a closet, a box we can barely turn around in while infinity stretches outside. The universe is not just unimaginably large, it is unreachably large. The difference matters. Size we can comprehend, unreachability we must accept, and the reason we cannot escape is written in the laws of physics themselves. Einstein published special relativity in 1905. Buried in the mathematics was a statement that changed everything. Nothing with mass can reach the speed of light. Not difficult, not expensive. Impossible. The energy required approaches infinity as velocity approaches light speed. Infinite energy is not available, therefore light speed is unreachable. The barrier is not technological. It is fundamental to space-time structure. Here is why. Mass and energy are equivalent. Einstein's famous equation, E equals mc squared. As an object accelerates, its kinetic energy increases. That energy adds to the object's relativistic mass. At 90% light speed, an object weighs twice what it does at rest. At 99%, it weighs 7 times more. At 99.9%, 22 times. The curve becomes vertical at 100%. Mass approaches infinity. Energy needed to accelerate further approaches infinity. You hit a wall built into reality itself. Particles without mass travel at light speed naturally. Photons, gluons, gravitons if they exist. Zero mass means they must travel at light speed. Cannot go slower, cannot go faster. Locked at exactly 300 million meters per second. Add any mass, and the speed limit drops below light. Even a single electron cannot reach light speed. Too much mass. The barrier applies universally. No exceptions, no loopholes, no clever engineering around it. Some physicists proposed exotic solutions, warp drives, Alcubierre metrics, contract space in front of the ship, expand space behind it. Create a bubble of normal space-time carrying the ship faster than light without the ship actually moving through space. The mathematics work within general relativity. The physics are horrifying. You need negative energy, exotic matter with negative mass. Nothing like this exists. Quantum field theory allows tiny amounts under specific conditions. Scaling it up to spaceship sizes requires more negative energy than positive energy in the visible universe. The numbers are absurd. Wormholes offer another theoretical path. Shortcuts through space-time. Connect 2 distant points through a tunnel. Step in one end. Emerge light years away instantly. The Einstein-Rosen bridge solutions exist mathematically. Keeping wormholes open requires exotic matter again. Enormous amounts. The throat would collapse without it. Plus, nobody knows how to create a wormhole in the first place. The solutions exist on paper. Nature does not provide them ready-made. We would need to engineer space-time itself. Technology infinitely beyond anything we can conceive. Time travel creates causality problems too. Faster than light travel is mathematically equivalent to time travel in certain reference frames. Travel faster than light, and you can arrive before you left from another observer's perspective. Send a message to the past. Create paradoxes. Kill your grandfather before your parent is born. The universe seems designed to prevent these paradoxes. The light speed barrier might exist specifically to protect causality. Break the barrier, and you break time. Physics does not allow it. Some quantum effects appear faster than light. Quantum entanglement. Measure one particle, and you instantly know something about its partner, regardless of distance. Einstein called it spooky action at a distance. Experiments confirm it works, but no information travels faster than light. The correlation exists, but you cannot use it for communication, cannot send messages, cannot transmit energy. The effect is real but useless for beating the speed limit. Nature is tricky. Gives you phenomena that look like faster than light effects but are not. Tachyons are hypothetical particles that always move faster than light, never slower. They exist in some mathematical frameworks, never detected experimentally. Most physicists think they do not exist. If they did, they would create causality violations, negative energy states, unstable vacuum. The universe would behave differently. Observations show no evidence of tachyons. The theory is interesting. The reality is absent. Hyperspace is pure science fiction. No physics supports it. The idea is moving through a higher dimension where distances are shorter. Drop into hyperspace. Travel 1 light-year there while only crossing 1 light-hour in normal space. Exit hyperspace far from your starting point. Nice in stories, impossible in reality. We have no evidence for accessible higher dimensions. String theory proposes extra dimensions, but they are curled up at microscopic scales, not exploitable for travel. Hyperspace is fantasy, entertaining but false. The light speed barrier stands because space-time has a maximum rate of causality. Information cannot propagate faster than light. Cause and effect have a speed limit. This is baked into the universe's structure, not an engineering challenge, not a technological limitation, a law as fundamental as conservation of energy. You cannot engineer around it any more than you can engineer around mathematics. 2 + 2 = 4. Light speed is the maximum. These are not suggestions, they are facts. Every observation confirms the barrier. Particle accelerators slam protons together at 99.99999% light speed. The particles gain energy. They do not gain more velocity past a certain point. Mass increases instead. Energy goes into relativistic mass, not speed. The curve never reaches 100%, cannot reach it, will never reach it. Billions of experiments over decades, same result every time. The limit holds. This leaves humanity in a bind. The stars are light years away. We cannot travel light years in reasonable time. We cannot reach light speed. The math is merciless. The physics unforgiving. We can see destinations we can never reach. Know they exist but cannot visit them. The universe is transparent. Our speed is limited. The combination is torture. Show us everything. Let us touch almost nothing. But assume we accepted this and planned anyway. We still face biology. Grizzly bears sleep for 7 months straight. Heart rate drops from 55 beats per minute to 9. Body temperature falls from 99 degrees to 88. Metabolism slows to 25% of normal. The bear does not eat, does not drink, does not urinate, does not defecate, survives on stored fat through an entire winter, wakes up in spring ready to function. No permanent damage, no health consequences. Evolution solved the problem of surviving resource scarcity through suspended animation. Scientists at Washington State University studied hibernating bears using gene sequencing. They discovered thousands of genes that activate only during hibernation. These genes protect muscles from atrophy, prevent bone loss, maintain organ function. The bear's body shifts into a different biological state, not sleep, not unconsciousness, something else. A programmed metabolic reduction that preserves health through months of inactivity. Humans have some of these genes, evolutionary remnants from ancestral mammals, mostly inactive now, potentially reactivatable. NASA funded research into inducing hibernation in humans, reduce metabolic rate, lower body temperature, slow biological aging. A crew hibernating for most of a journey would need less food, less water, less oxygen, less living space. Resource requirements drop dramatically. A 10-year mission becomes feasible with 5 years of supplies if the crew sleeps for 5 years. The math makes long missions possible. The biology is uncertain. Cooling humans safely is the first challenge. Lower body temperature too fast and ice crystals form. Cell membranes rupture. Tissue dies. Therapeutic hypothermia in medicine cools patients a few degrees for hours, not months, not years. Extended cooling requires preventing ice formation, maybe using antifreeze compounds, maybe using pressurized environments where ice cannot form. Research shows promise. Practical application is years away, maybe decades. Muscle atrophy presents another problem. Astronauts on the International Space Station lose muscle mass rapidly in zero gravity. Hibernating would worsen this. Bears avoid atrophy through specific gene activation. Humans lack this natural protection. Pharmaceutical interventions might help. Drugs that preserve muscle during inactivity exist for medical use. Extending them to months or years of hibernation is untested. The side effects are unknown. The effectiveness is uncertain. Bone density loss compounds with muscle loss. Weight-bearing activity stimulates bone growth. Remove activity, and calcium leaches out. Bones become brittle. Osteoporosis sets in. Astronauts on long missions take bisphosphonates to slow bone loss. Works partially, not completely. Hibernating crew members would need stronger interventions. Maybe gene therapy. Maybe nanomachines maintaining bone structure mechanically. All speculative, none proven. Immune system function drops during hibernation in animals. Infection risk increases. A hibernating human crew would be vulnerable to any pathogen. Sterilizing the spacecraft helps but is not perfect. Bacteria